Hey everyone, so I want to move on to the next really big section of this topic, which is friction. This is another one of those things where we're going to be constantly coming back to it, not only in this topic, but in later topics as well, since friction is going to be a huge thing. Now, one thing I want to point out is that you want to keep an eye out for some hints and tips that they usually say that kind of hint that there's going to be some sort of friction. One good example is that they sometimes will say the phrase rough surface. If they ever say that phrase, that a block is on a rough surface, obviously that's a hint that we're going to have friction as opposed to being on a smooth surface, which usually hints that there's no friction. Like I said, a lot of times the questions don't blatantly say there is going to be friction. Sometimes they'll casually throw it in there. Other times, another phrase that they could use is uh, they can give details about the specific materials involved, as we'll see later, since the material itself is dependent or does affect how much friction we end up having. You should have noticed by now that a lot of the questions that we end up getting are very vague questions. It's an object on a table, but if you start seeing them say something like it's a copper block on a copper table, that usually hints that there's a little bit more involved. And again, the material hints that there's friction. There's a second or a third thing that they could do. If you do the problem, or assuming that it was frictionless, if you come across a scenario that kind of almost contradicts what should happen, that hints that there's going to be friction. For example, if I make a comment that uh, I have a box on a table and I apply a 5 newton force to it and it's moving at a constant velocity. Now, if you go to draw the FPD, there are only three forces going on. There's gravity, the applied force, and the normal force. But here's the issue. Because of Newton's first law, we know that since the velocity is constant, all these forces should be balanced. Fg and Fn get balanced, but there's nothing balancing the 5 newtons. So when you're doing the problem, you'll go, okay, so I guess there must be friction in order to make sure that this is balanced. Typically, you wouldn't be in a weird situation where it could exist without friction, without them giving some other hint. All right. So, what is friction? Well, we actually mentioned this already when I briefly talked about the different types of forces. Friction is something that opposes motion. Now, there's one aspect of this that makes really a lot of sense, that if we're moving in a certain direction, friction is always going to be in the opposite direction. So if we're moving something to the right and it's moving in that direction, then friction is going to be to the left. If we're throwing something up, friction is going down. However, the other thing that I want to point out is with this phrase opposes motion, it also refers to opposing the, I guess you could say, the threat of motion or the possibility of there being motion. A good example of this one is I'm going to do pretty much the same scenario. I have a box on a table and I push it to the right with 5 newtons, but the object doesn't move. It is at rest. We know that since the object is at rest, again, because of Newton's first law, that there has to be a force in the other direction. Since the object would be moving to the right if it was a frictionless setup, if there was no friction, then that means friction would have to oppose that threat of moving to the right by pushing to the left. So that's another thing that we mean when we say opposes motion, that not only is it opposing the direction it currently is moving in, but also that it could be moving in without friction. Typically, friction comes across from the objects or surfaces rubbing against each other. There's also air friction where the material rubs against the air particles. In particular, the reason this is coming about, I'm not going to get too technical with it, but when you look at a material in like underneath a microscope, you'll see that there's all these bumps and grooves in the material, and certain materials have more bumps and grooves than others. If you take two materials that have bumps and grooves together and you place them up against each other, when you try to slide it, there's going to be a situation like this where one set of grooves meets a bump of another one, and it almost catches on and resists and causes there to be some sort of resistance to sliding them. So that's kind of where friction's coming from. A scenario where there's not much friction would be where one of the surfaces is essentially flat, where there are no bumps and grooves to latch onto. So that's why walking on a sheet of ice can be so slippery, because even though your shoes have all these bumps and grooves on them, the ice doesn't really have it. This also explains why oiling something up or putting some sort of liquid material in between the two surfaces also ends up causing it to slide easily and decrease the friction. Because when we place, let's say, try to draw this, we have a surface like this that has a lot of bumps and grooves. If we fill in the bumps and grooves here with some sort of liquid, now it's not as bumpy and groovy like that. It becomes a lot flatter. So when it comes into contact with another surface that is still bumpy and groovy, the liquid acts as a barrier to smooth it out a bit, resulting in, again, not as much of the bumps and grooves catching on and latching on and resisting your motion. So this is what's going on. It's all that imperfections at the microscopic level that's going on. We can improve friction by oiling it to fill in the gaps. We can sand it down to get rid of the bumps. That's pretty much the idea behind it. There are two main types of frictions. Actually, I shouldn't say there's two main types, because there's only two. There is static friction, which is the friction that we end up getting when an object is at rest. So again, we mentioned before that if we apply a force onto an object, there's friction that's opposing that motion, keeping it from moving, and we call that static friction. If I keep pushing on an object and actually start getting it to move, I end up getting what's called kinetic friction, where this is where the objects are experience when they're in motion. Again, this kinetic friction is slowing the object down. So static friction is keeping it at rest, while kinetic friction is slowing it down. Again, we can kind of look at it at the microscopic level as to what's causing this. In the static case, the bumps and grooves have had enough time to basically fall within each other. So we have all the bumps and grooves, and then the other bumps and grooves, they have enough time to kind of latch on and get in real tight of a connection there, making it really hard for it to kind of push against the other. When we're talking about kinetic, because the object, oh, I should probably draw it a little bit better. Because it's moving, they're going to be still hitting the top. So even though they could latch on, they're not latching on enough, because essentially the momentum of the object is keeping it from falling in too much into each of the bumps and grooves. Again, you don't really need to worry too much, but it's kind of how you can visualize what's going on at the microscopic level. All right, so we come up with the frictional equation. Friction arises between the two surfaces rubbing against each other. As we kind of described, because it's based off of how bumpy and groovy the materials are, a measurement of how bumpy and how many grooves the surface has will affect the friction. The more bumps it has, the more the friction there will be. The smoother it is, the less friction. We can see this with a bunch of different objects. But there's a second thing that actually affects how much friction we get, the amount that they're in contact. You could do this yourself right now, where you take your hands, you can clearly see the bumps and grooves on them. If you slowly and very lightly brush your hands together, you won't really feel a whole lot of friction. Now, if you remember, or if you know from any time being cold, you can rub your hands to get a little bit of heat, and that heat is caused by friction. Well, if you rub your hands very softly, you don't really feel any heat coming from your hands. But if you push your hands really hard, you will start to feel that friction coming across. You'll start to feel your hands heating up a little bit more. So the amount that the two surfaces are in contact will also increase your friction. Now, what force is considered a contact force? It's the normal force. So what we end up having is an equation that looks like this. F of F is our frictional force. This is measured in newtons. Mu, that's what this symbol represents. It's a Greek letter. You could just write a U and then draw a line right down the middle, right down the front, sorry, is the coefficient of friction. It's basically a description of how rough the surfaces are. And Fn is the normal force. Now, I want to actually clarify one thing about this. You may notice that this equation looks a lot weirder than all the other equations we have. First, there's this less than or equal to sign, and then there's also these absolute value brackets. So I want to explain this a little bit. Before I do that, I want to make a quick statement. If you look at the equation for the net force equation, you'll see that it looks like this. Oh. So you'll see F net equals ma with F net and A having these little arrows above it. I should have mentioned in a previous video that those arrows are there to show that these are vectors, as opposed to mass, which doesn't have an arrow, that's a scalar. Now, this doesn't really play that huge of a role in AP physics, but when you go off into college physics and higher level physics, this equation actually this is an important notation, that knowing what variables are and aren't vectors. In particular, because there's only one vector on the right hand side and only one vector on the left, this equation is actually telling me that these two terms, F net and acceleration, are in the same direction. If A is to the right and we make it a positive number, then that means that F net will also become positive since since M is a scalar and doesn't have a sign. F net will also be positive and therefore be in the same direction. This is in contrast to this equation dealing with springs. We haven't learned this one yet, but you will, where we have these two terms, Fs and X. Both of these are, once again, vectors, but this time, because there's this negative sign, if I make X positive, saying that it goes to the right, now Fs is becoming a negative term, because K, once again, is a scalar and has no sign. So this negative in this equation tells me that it's in the opposite direction. Now let's come back to this one. If I draw an FBD, the normal force always acts perpendicular to a surface. So this is the direction of the normal force. My friction only acts parallel. So it's going to act either to the left or to the right. Now, these two are not in the same direction. So I can't just leave it like this, and they're not in the opposite direction, so I can't just add a negative. These two are in completely different dimensions. So what this equation is saying, by placing these absolute value brackets, is that the reference table and the AP is trying to convey that the magnitudes are the same, but that doesn't mean we could get any information about direction. Going back to these equations, if I know the direction of acceleration, I automatically know the direction of force. If I know the direction of X, I automatically know the direction of the spring force. Coming to here, just because I know the direction of the normal force doesn't mean I know the direction of the frictional force. It could be in two different directions, left or right, or anything that's perpendicular to my normal. So that's why we place these absolute value bars. Do you need to do it? No. The AP just does it for convenience sake, for like I said, to convey this concept, this idea. But if you're drawing an FBD before all your problems and you're doing everything like that, then you're already taking into account direction in the equation. You're going to be making things positive and negative, and basically you're using the equations in terms of magnitudes only and not to get direction. So I just want to point that out there, that you're not going to really see me placing the absolute value bars in it, because of the fact that, again, I'm taking into account direction already outside of the equation. As far as the less than or equal to sign, I'll get to that in a second. So going back to the coefficient of friction, I said before that it's a measurement of how difficult it is for the two materials and surfaces to rub. First, coefficient requires two materials. You can't just have a coefficient of friction for your cell phone. It has to be your cell phone on a certain surface. So the cell phone on metal or a cell phone on wood. Those will have a coefficient of friction. A high coefficient of friction usually means that it's harder to rub and that the surfaces are really rough. I should say both are rough. A low coefficient of friction means that it's easy to rub and that the surfaces are both smooth, or at least one of them is smooth. Now we can ask ourselves, what are the units for the coefficient? Well, if I look at my equation again, the equation is f of f is less than or equal to mu Fn. Well, f of f is newtons, f of n is newtons. The units on both sides of the equations need to balance out. So that means since I already have newtons on the left and newtons on the right, mu must be unitless. So there are no units for mu. Keep that in mind. Now, I mentioned before that there are two different frictions, static friction and kinetic friction. These aren't just names, they are actually completely different values. The kinetic friction on an object is different than the static friction on that same object. So since we only have one equation, that means the only thing that can be different in the ff equals mu Fn, since Fn is going to be the same, mu is the one that's different for the two types. So we're going to have two different coefficients, a coefficient for static friction and a coefficient of kinetic friction. Just like their frictional counterparts, these coefficients get used for being when the object's at rest, in which case we use static, or when it's in motion, in which case we use kinetic. Now I'm going to start with the kinetic one since that's easy. As I mentioned, the equation is less than or equal to. If we're using the kinetic coefficient though, we actually don't need to include that less than or equal to. It's just going to be straight up equal sign because the kinetic coefficient doesn't change. No matter how much I'm pushing on it or what the mass is or whatever, the kinetic friction on an object remains the same. As long as it's in motion, it will experience a kinetic force of some value. So if I'm pushing on an object with a force of 5 newtons and I know that the kinetic friction is 3 newtons, then it's going to be 3 newtons. If I apply a force of 10 newtons, the kinetic friction is still 3 newtons. If I apply 1 newton of force, the kinetic friction is still 3 newtons. The kinetic friction doesn't change. So that's that. Now here's the thing with the static. So the static, when we use the coefficient, we actually get the maximum force that can be applied before the object begins to move. What I mean by that is this. Let's say I use the equation ff equals mu Fn, and I get that the static friction is 14 newtons. What this number is telling me is that I can apply any number up to 14 and the object will remain at rest. But here's the issue. If I apply a force of 5 newtons and the object is at rest, does it make sense for my friction force to be 14 newtons? No, because according to Newton's first law, these forces are not balanced. 14 is bigger than 5, therefore it's unbalanced and not in equilibrium. So according to Newton's first law, if the force on the right is 5 newtons, then this force also has to be 5 newtons. Since this number is less than 14, that means my object will remain at rest. If I increase this to, let's say, 10 newtons, then again, the frictional force will have to keep it at rest, and this one will also increase to 10 newtons. And I can keep doing this until I get to 14. Once I bypass the 14 newtons, my object will slip and begin moving, in which case the kinetic coefficient comes about. So because of the fact that the static friction is a max value when we use this equation, that's the reason why we give it a less than or equal to sign, to remind ourselves that the number we get when we use static friction, That is the maximum number that can be applied before it moves. But it could be any number between 0 and that static friction. So again, if I apply 14, if I have a static friction of 14, whatever the applied force is, if it's less than 14, then my frictional force is going to balance that. And so that's something that you have to kind of keep in mind. Sometimes what they'll do is they'll throw in and ask about, the maximum force that could be applied, basically hinting that you're using the max value of this static friction. But you're going to see a few examples of this. Always remember, Newton's first law always holds true, that if the object is at rest or moving with a constant velocity, the forces must be balanced, regardless of what's going on with the force equation, the frictional force equation. It's important to note that if you see any problems, they're usually going to give you the coefficients, or they'll be asking you to find it. You don't need to memorize these. There's literally thousands of them, so you're not expected to know them. You may notice some of the questions that I do, though. I throw in some the Regents physics questions. The physics reference table actually includes a little chart of all the coefficient of frictions. So you might see some problems where they start mentioning surfaces. Just pull up a Regents reference table, look at the front page for that chart, and use those numbers. But anything related to AP style, they'll usually give you the frictions. So you might notice a few questions like that in the video that require a reference table. One thing that actually is always useful to remember is that the static friction is always greater than the kinetic friction. This basically means that it's always harder to start the object to move than it is to keep it moving. And as I said, this goes back to the idea where when you're starting the object to move, the bumps and grooves have had time to basically fall into each other, to kind of latch in and sink into each other, to make it really hard for you to overcome that static. But once you overcome it and you basically move it off of the bumps and grooves, now the bumps are kind of riding at the tops and feeling just a little bit of the friction, not feeling all of it. There's a very common graph that you might see where it's the force of friction that a block will experience versus an applied friction. So in the beginning, when the object is not moving, as we know, the frictional force and the applied friction will balance out. So if I apply 5 newtons onto an object, friction's 5 newtons. I apply 10 newtons, the frictional force is 10 newtons. And this is going to keep going and going until I reach that maximum static friction possible. Once I hit that and it begins to move, all of a sudden the kinetic friction takes over. But because the kinetic friction's lower, that means the graph is going to drop to about a lower spot and then remain constant. So if I'm applying a force that's less than the static friction, it's essentially constant, or increasing, sorry, equal to whatever I apply. I reach this max point, which is my static friction. And then once I surpass the static friction, the kinetic friction drops and goes a little bit lower. And this is where I start moving. So you might see this in a few labs. I just want to throw this out there, that if you ever see this graph, that's what it's referring to. The fact that the frictional force changes depending on the scenario. All right, we're gonna pause the video here. We'll do some more. We'll do some practice questions in the next video. I just want to kind of lay out the concepts behind it. But you can watch the next video where I go into detail and show you some practice examples. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.